Hello and welcome everyone to today's webinar. My name is Lauren Harrington and it is my privilege to be the host of today's webinar. Joining me, we have a very special guest speaker with a lot to say about everyone's favorite class of exploding binary stars. But before we get into it, I do have a few quick announcements to make. First, I would like to point out a few features here inside Zoom webinar. If you take a look down at the bottom of your Zoom window, you should see a few buttons. There's the chat box where we've all been introducing ourselves. There's also the CC or closed captions button, which allows you to enable or disable Zoom's automatic closed captioning. And there's an extra button down there labeled Q&A. If you click on the Q&A button, you will have the option to submit questions for our speaker. You can submit as many questions as you would like at any point during the presentation. Don't worry, it's not going to interrupt the presentation when you submit a question. After the presentation, we have some time set aside for a Q&A session, and we will try to answer as many of your questions as we can fit in. All right, good news. Registration is now open for next month's free webinar. This is a particularly special one. The presenter will be none other than the executive director of the AAVSO himself, and he plans to talk about photometric filters and transformations. Filters and transformations might just be the topic that we receive the most questions about, so we're very much looking forward to May 11th when Dr. Brian Kloppenborg will clear things up. You can learn more and find the registration link on our website at aavso.org/webinars. Now, I would like to thank our 2024 series sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their website to learn more about their work. All right. Now, those of you who attended our latest annual meeting will recognize today's speaker as the highly esteemed Landolt lecturer who started off our proceedings on Saturday morning with an outstanding presentation. For those of you who haven't yet had the pleasure of meeting her, today's guest speaker is a professor in the Department of Astronomy at the University of Washington, where her research focuses on close binary stars with active mass transfer, also known as cataclysmic variables, or CVs. In her work, she uses a multi-wavelength approach, combining observations from space-based observatories, such as the Hubble Space Telescope, with ground-based facilities all over the world. Recently, she has been pushing the boundaries of knowledge by finding the faintest, lowest mass transfer rate CVs, leading to new insights about such topics as the nature of mass transfer and accretion, accretion disks and their X-ray emission, stellar coronae, and even the effects of irradiation on the upper atmospheres of late-type secondary stars. Now, that is thoroughly fascinating stuff. And personally, I cannot wait to hear what she has to share. So, without further ado, I'd like to introduce our esteemed guest speaker, Professor Paula Szkody. Welcome, Professor Szkody. We're very glad to have you here.
Hello, everyone. Welcome and glad you could make it on this spring Saturday morning. And thanks, Lauren, for that introduction and for doing these series of webinars. I've attended several and they're very, it's wonderful to hear from all the people that are doing work on variable stars. All right, today I'm going to try to give you a grand tour. It's not going to be a complete tour because there's just too many. I'm going to try to get thumbnails video out of the way. There's so much going on with cataclysmic variables, and that's why I love them. Every time we think we know how they behave, they do something different. And that for me is the fun. I've been doing this for 50 years and it's never a dull moment. And I'm always finding new ones. So it's just great. Okay, let's see if I can. My slides will not advance. What am I doing wrong here? Lauren, do you have a clue as to why I can't advance my slides?
It's possible that Zoom has focus instead of PowerPoint right now, since you dragged that window out of the way. Um,
So what should I do?
so are you on a Mac or a Windows machine?
A Mac.
Okay. If you
Oh, wait a minute. Let me try the bottom. Oh, okay. I'll just use a little arrow on the bottom.
okay,
That
that
seems to
works.
work. Okay, my screen. Okay. Okay, good. So basically, I'll just start out with some basic parameters. I think a lot of you know a lot about CVs, but for those that are new to the field, this is the basic definition of a cataclysmic variable. It's a close binary, and by close, I mean the two stars are separated by about the diameter of the sun. The primary star, the more massive star, is a white dwarf. And the secondary star is a low mass secondary, which is usually an M star, but could even be a G or K star in some cases, or a brown dwarf in other cases. But mostly it's M stars. And the criteria is that it has to be actively transferring mass. Now, sometimes that mass stops, but other times, most of the time it's actually transferring mass. There are various ways of describing cataclysmic variables. And I'm just going to go through a couple of them. One way is by their variability. And just look at the last two columns on the right here. The time scales vary from seconds all the way to basically 10,000 years for novae. I'm not going to talk about novae today because I can't cover everything. And so, but there's very long time scales involved. So every time scale that you want to explore is here in cataclysmic variables. And the amplitudes range from hundredths of a magnitude in some cases up to basically 15 magnitudes for novae, and basically up to 9 magnitudes for dwarf novae. The way I like to really classify them is instead by magnetic field properties. Most of the objects we know have disks, so the mass transfer occurs from the secondary star and accumulates in a disk, which then accretes onto the white dwarf. And we know more than 5,000 of these kinds of systems right now. And they are perhaps the easiest to identify in light curves because of their outburst behavior. The disk builds up and creates what we call a dwarf nova outburst. But nova-likes are also in this category, and they don't have outbursts because the mass transfer rate is too high for outbursts. But this is what they would look like if we could ever visualize. I was hoping that ultimately in the interferometers, et cetera, we would be able to actually get a picture of a CV, but that hasn't happened and will not happen for a long time because they are very close together and far away. We can't resolve them. If the magnetic field gets higher, so most of these we think are under a megagauss because we really don't have any way to measure a good field that's kilogauss, values of magnetic field. But once we get to the 1 to 10 megagauss, we can actually see some Zeeman features in the spectra, and we can actually try to get some idea of the field. So these systems, the magnetic field prevents the material from going down to the white dwarf in the accretion disk, and instead creates like a hole, and the material goes along the magnetic field line. So most magnetic fields are dipole fields. So you'll see like two streams, usually one underneath the disk and one over the disk, depending on the orientation of the magnetic field to the plane of the binary. So these things are called IPs, or intermediate polars. As you go to higher fields, then you come into the regime of the polars. And these have fields from 10 to 250 megagauss. And there the magnetic field is so strong that it governs the entire space out to the secondary star. And so the material as it comes through as a ballistic stream and goes directly to the magnetic poles. And it can go to one pole, as in this case, or it can actually go to two poles. So sometimes that stream can go around and have two poles accreting at the same time. And this last category that is really one of my favorites are called low accretion rate polars, LARPs. And there's only about 36 of these known now. Recently there's been an addition of like 15 of these from the Zwicky transfer facility, transient facility. And these have the same kind of strong fields as polars, but the accretion rate is so weak that the mass transfer rate is basically from a wind, and then it just accretes on various magnetic areas of the white dwarf. And the way that the accretion happens is really important and gives, different characteristics in the light curve. If it's a disk accretion, and it depends on whether the accretion rate is high or low. So this m dot is the mass transfer rate. You can think of it if it's even mass transfer, then it's mass accretion rate. If the accretion rate is very high, then the disk is very thick and produces most of the light of the system, which means it hides the stars. You can't really see the white dwarf or the secondary star. Where the disk meets, I keep losing my question, where the disk meets the white dwarf, there's a difference in rotational velocities there. And so there's this big, what's called a boundary layer created, and that can create a lot of high energy radiation, which is mostly seen in the optical mostly seen in the UV and the X-ray rather than the optical. If the mass transfer rate is low, then the disk is not so important, and you can actually see the white dwarf. And I'll show you some examples of that. We detect that from the spectra mostly, and we can see changes in state between outburst disks on the left here and quiescent disks on the right. So the disk in quiescence just builds up and builds up until it starts to look like this in an outburst. And in nova-likes, which don't have outbursts, the disks are basically in this high m dot state all the time, but for some reason that we don't understand yet, that the accretion turns off completely, and then basically the disk pretty much goes away, and then you get to see the white dwarf and the secondary star. In magnetic accretion, those are the ones where the stream is hitting in a shock at the white dwarf, at the poles of the white dwarf. You get different kinds of emission happening. There, it's basically the shock is right at the white dwarf surface, or in some cases buried into so this purple area here is the white dwarf. That shocking gets buried depending on the flow rate. And you have a lot of high energy stuff happening in this area, and that high energy stuff heats also the white dwarf photosphere and makes it hot. So all of the radiation that you get is basically from this shock area at the poles. And again, it can hide the white dwarf itself because there's so much light coming out from the pole areas. So there's basically three kinds of accretion properties, what we call an outburst. There's a novae, which I'm not going to talk about because that's a whole other field, because those outbursts are thermonuclear on the surface of the white dwarf, whereas the things I'm going to talk about today are basically a disk outburst. Material in the disk accumulates and causes a rise in accretion rate, which causes an outburst. And the nova-likes, basically, they don't have outbursts because they're always in this high accretion state. But as I said, for these unknown reasons, it turns off completely or partially, and then that creates what we call a low state. So nova-likes have high and low states. Dwarf novae basically have outbursts. Okay, so we can also subdivide. There's so much terminology in CVs. Even those that have disk accretion, we have these different states. So I've already talked about the nova-likes that have high and low states. But the dwarf novae have what we call normal outbursts. Then we have super outbursts, SOBs, and we have quiescent states. So they were basically three states for a dwarf nova. And then there are systems that we call Z-cam systems that have what we call standstills, where the light remains at high level, and therefore the accretion disk is still pretty intense, about a half magnitude or magnitude below outbursts. And then sometimes they will have outbursts as well, and they will have quiescent states. But the time scales for each of those states varies. And then we have ER-UMA stars, which have what we call supercycles between normal outbursts and super outbursts. And I'll show you some examples of those. All right, so Yoji Osaki, way back in 1989, was one of the theorists that was exploring all of the behavior of disks, along with several other groups. And he came out with this scheme. If you put in the accretion rate here, or the mass transfer rate, versus the orbital period here, you have the ones that have short orbital periods on the left here, under 2 hours, and those with longer outbursts, longer orbital periods on the right. And here are the types that I was talking about here. So you have the ER-UMA stars that are very close to this line. And this line is the critical mass transfer rate that keeps the disk in a high outburst state. So above this line, you're not going to have any outbursts. And so you have nova-likes here. And there's other category called permanent superhumpers, which have these, and I'll get into superhumps in a minute. But those are the ones that have basically high accretion rates. And then the ones that do have outbursts are divided into the normal UGEM stars, or SS Cygni, however you want to categorize them. Those are, if there is such a thing as a normal outburst, they would be in this category. And then the Z-Cam stars are right very close to this critical line. So that's what we think creates the standstill situation, because if they're pushed over this line, then they don't have an outburst, they just get into this standstill state. Whereas for the shorter period stuff, they have another aspect that they have to think about, and that is the tidal effects from being in a system where the difference in mass between the white dwarf and the secondary is a factor of 4. So if that ratio is less than a fourth, then you have these tidal effects coming into play, and that creates the stars that are called SU-UMA or WZ Sagitti stars that have super outbursts, and the ER-UMAs, which have super outbursts followed by normal outbursts. So that's basically the scheme that seems to work in terms of where all of these different objects sit in terms of their accretion rates and their orbital periods. So the outbursts are really important because they really do test disk theory. And this has been going on for a number of years. And there's been all these controversies. Well, is an outburst caused by mass transfer increases, or is it caused by, the buildup of the disk? And if we study the shapes of the outbursts, the shape during the outburst, the decline times, how long it stays at outburst, the width of the outburst, that gives us some clues for the modelers to go ahead and try to model an accretion disk. And then the recurrence times will vary based on the mass transfer rate. So if the mass transfer rate is very low, it takes a very long time to build up the disk. And so the recurrence of outbursts will be a long period of time. And then there's this thing about precursors to the outburst. So sometimes an outburst will start and then it will turn into a super outburst. And I'll show you some examples. So here's the classic example of a dwarf nova outburst. This is the light curve of SS Cygni, as you're probably all aware of, showing the tremendous variation in the way outbursts look over a period of over 100 years. So sometimes you have, most of them, the outbursts are pretty much the same amplitude, but then you have this weird stuff happening in the continuum in some cases, and then you have just some other, it gets interrupted here, and here's some faster outbursts occurring. So there's a tremendous variety, even in what we consider a normal outburst sequence. And so it's this presence of an outburst that makes it fairly easy to identify new cataclysmic variables. So I've been involved with the latest all-sky survey, which is the Zwicky Transient Facility that's run by Caltech from Palomar. It's a 48-inch telescope with a very wide field of view. And it was taking observations of basically the entire northern sky, first at every night, and then every 2 nights, basically. So we put together the observations over periods of time, and we look to see if there's anything that could be called an outburst, and that we can classify it as a cataclysmic variable. But this just gives you a somewhat idea of the range of things that we see for outbursts. So this would be like a normal kind of outburst situation in SS Cygni. This would be these two would be super outbursts, and this is the characteristic shape of a super outburst. It's a rapid rise, and then there's kind of this plateau that lasts for a few weeks, and then it can decline. And then you can have these, what we call echo outbursts. And here's also a situation where it's not so clear whether this is a super outburst. And then there are these other ones, which could be either echo outbursts or just normal outbursts happening after a super outburst. And then this one here's again, there's a plateau and then the decline. So this is what we look for in the light curves in sky surveys to try to figure out, is this really a CV or not? The better way to do this, or one of the other ways to do this, has been with the constant sampling that's been happening with the space satellites. Kepler sampled for 5 years, and here's one of the classic examples from that survey is V344 Lyra, which shows the tremendous detail of super outbursts and normal outbursts. And this is just a blow up of this is in flux on the left, and this is in magnitudes, Kepler magnitudes on the right. Kepler is mostly a reddish CCD, so you're getting kind of a reddish amplitude for the outbursts. And this top one is just the total length of time, and you can just see the tremendous range of outbursts and super outbursts. So you can see in the flux plot, which has a different way of representing the light, and you can see some of the super outbursts, super humps happening. So and here's a precursor. So as I was saying, it's at quiescence and it rises, and it looks like it's going to go to just a normal outburst, but then there's an extra kick, an extra mass transfer, and it rises to a super outburst. And then these super humps develop, this variability. A super hump is basically, the disk becomes elliptical and precessing, and it causes a period that's a few percent longer than the orbital period. And these things have very large amplitudes and easily detectable. You can see those happening in these super outbursts. Now, the super humps are very interesting. They've been, it was unknown for a long period of time what was causing them, but I think now they're fairly well understood as coming from this precessing elliptical disk. When the mass transfer rate reaches when the disk size reaches a certain critical radius, they start to develop. But one of the interesting things is that some of these super humps that have been seen can last for long periods of time, and they are called, that was the PS in the diagram with Osaki that I showed. These are the permanent super humpers. It happens in fairly rare cases, and in some cases, particularly this object that we worked on in way back in the 2000s, it has positive super humps when it's bright near the outburst, and a positive super humps just means that the period that you see in the light curve is a few percent longer than the orbital period. But then when it was in quiescence in October, these super humps had larger amplitude, and they were a period shorter than the orbital period. So this is called a negative super hump. And the theory behind that is that if the disk becomes tilted out of the orbital plane, then the period that you see is shorter than the orbital period. So super humps are, kind of an interesting thing. And they are, known at some level, but why some systems develop these negative super humps and others don't is still not totally understood. Standstills are another interesting phenomena that happens for those systems that are very close to that critical mass transfer rate. So Janet and I did a study of all the AVSO light curves way back in the 80s, and this is one of my favorite pictures of a standstill. ZCAM can have standstills that last for years. I don't know if you can read all the vertical here. This is 100 days. It's lasted a long time. And I really like this buildup. I've been trying to get the theorists to come out with a reason why the disk builds up, never quite returns to quiescence, and then goes into the standstill. So it's just getting close to that critical value. And other systems like V513 CAS have very short standstills in here versus the long ones that are apparent. And here you can see that here it was kind of build up down to quiescence. Each dip went down lower than the previous one. So there's a lot still left to be done for standstill situations. And then the ER-UMAs, these are the ones that have supercycles, which is a repeatable time frame. There's about 6 or 7 of these known now. And it just takes long monitoring to pick up the supercycles because the supercycle length is quite long. So in these kind of systems, they will have a super outburst, and then they will have a series of normal outbursts, and then the same, another super outburst, and it repeats on a given cycle. And so again, it's being close to that critical mass transfer line and so there aren't very many objects that are close to that line. And so there's not so many of these kind of systems known. And then another one of my favorites is the systems that have really large amplitude outbursts. GW Lieb and V386 SIR are a couple that I have followed, and here's the AVSO light curves of those. They are, 9 magnitudes. That's the equivalent of a recurrent nova. And because the timescales for these outbursts in these systems that have these extreme amplitudes are very long, because it takes a long time to build up, but when it builds up, it really goes off from the quiescent value, which is low m dot system. And then when the disk has built up, it reaches this very large amplitude magnitude. So GW Lieb had one 1983, and then the second one in 2007. So if you believe this 24-year difference, we'll have to watch for the next one in 2031 to take place. And V386 SIR, it's been followed for many years, over 10 years, and we just had the first known outburst in 2019. Some of the systems in these ones that have very infrequent but very large amplitude outbursts, and WZ Sagitti is another one of those, can show what we call echo outbursts on the way down. So the light curve is that, that shelf for a super outburst. It starts to decline, and then the disk gets hung up at some intermediate value and kind of returns back to its outburst state before it finally decides it's done with this, and it returns back to its quiescent value. This happens in only some of the short orbital period systems. These are all very short orbital periods with the large amplitudes. The shape of the outburst tells the disk people a lot about what's going on. So the theory for disk for the development of an outburst is if it's a symmetric outburst, which is this first one, that means the outburst starts to heat up the disk from the inside of the disk out, and that happens in a low mass accretion scenario. The next outburst is a little less symmetric, so it has a steeper rise and then a more gradual decline, and that usually happens when it's an outside-in outburst, so the disk starts to heat up from the outside, and the wave travels inward. And then there are some that have this weird, it starts to have an outburst, and then something happens in the middle here, and it truncates the middle part of the outburst. And this is what we saw in one of my favorite objects. This was discovered in the Sloan Digital Sky Survey. And then it was followed by the Kepler-2 satellite. So we have a long string. Kepler-2 was a replacement once the original Kepler could not stay in its pointing at one field. It started to move around the ecliptic for a couple months at a time. So we still had long stretches of data. And you can see in this case, so this is flux, not magnitudes. But basically a factor of 2, like the magnitude changes in these little outbursts that happened before, and then it went into one of these truncated outbursts. And then look at the difference between the activity level prior to the super outburst and afterwards. So before, the amplitude of these mini outbursts is larger than afterwards, and the disk flickering or just general variability, this is not periodic, is much higher in the quiescent level before the outburst than afterwards. So again, this is an area where the theorists have not completely decided what is happening. And look at the shape of the outbursts, these mini outbursts afterwards. They're very asymmetric. So there has not really been any, output of, theoretical output of what exactly is happening to create this kind of a light curve. One of the best ways we have of classifying what an object is in this whole category of polars, intermediate polars, etc., is to use the spectra. And unfortunately, most of the objects at quiescence are faint, and so you need fairly large telescopes. The Sloan Digital Sky Survey took place. These were 1-hour exposures with a 2.5-meter telescope that surveyed most of the northern sky objects. And that went on for 8 years. And we found somewhere close to 300 cataclysmic variables. And then Keith Innight, a graduate student in England, continued this for the remaining part of the Sloan survey that went on from 2008 to 2020 and found a couple hundred more. So we have spectra of 500 CVs total. And what this shows is that you can identify from certain features in the spectra what kind of an object it is. And one of the most useful features is the helium-2 4686 line. So here it is. Here, these the spectra of CVs at quiescence are basically in Balmer emission lines with H alpha, H beta. But for a few of these objects, you can see this extra emission line shortward of H beta, and that's helium-2 4686. And so those are an indication of high excitation, which means a shock. And so that is one of the classic indications of a magnetic CVs, either an IP, you can see it here, or a polar. It's there in basically all the cases, except for the ones that have what we call cyclotron features. And those are very low mass transfer. Those are basically the LARPs that I showed you in that picture. And these cyclotron humps come in because electrons are spiraling in the magnetic field lines at very high magnetic fields and very low densities. And so those show up. The other thing that shows up, if you see this big absorption dip around the Balmer lines, especially in the higher order lines, the shorter wavelength lines, that's an indication that you're actually seeing the white dwarf, because the disk is thin. So it's an indication of a very low M dot system, and you're actually picking up the white dwarf in it. Okay, so there's a lot of orbital variations. I'm going to kind of speed up here. The orbital variations can tell you a lot about the orbital period from the eclipses. It can tell you if hotspots are present, reflection effects from the heated white dwarf, and as I said, the orbital period. So most of you are probably familiar with light curves, what the orbital variations. The nice thing about CVs is that the orbital periods are generally short, so you can follow during one night, you can get a couple orbital periods and easily identify if systems are eclipsing. And here's this big hot spot coming in, you can see. So it's very, very obvious when it's there that you're looking at gives you an idea of the inclination of the system. These would be high inclination. And lately we've been using ZTF, but we're using combination of the sky surveys, the long period. So this goes from basically several years of data from ZTF at Palomar. You can run a Fourier transform on it and get the orbital period, even though it doesn't look like anything much in the long-term light curve. But because there's so much data, you can basically fold back and get out the orbital period. So we got the period here from the ZTF data, and then we took spectra. And here's again the 4686 line. So that tells us that it's a magnetic CV. And then if you do follow the spectra around an orbit, you can actually get the velocity information, how much the line shifts, the helium line and the Balmer line shift in wavelength over the orbit. gives you a velocity variation. And look at, I don't know if you can see the numbers here on the left, it's 500 kilometers per second. This is a huge shift. And that is what's typically happening for a polar because of the velocities involved in that shock. So we can get very nice information from both the spectra and the light curves. I'm just going to quickly go through some of the light curves that we can see for some of the systems. This is for one of the ones that has an absorption around the Balmer lines in the spectra, and we can see the white dwarf. Now, it just turns out that for white dwarfs that are CVs, they're generally hot. They're like 12 to 15,000 degrees. And so they are in a zone of instability. I think a few months ago, there was a talk on pulsation modes. The instability strip for CVs is much hotter than normal because of the mass transfer, creating different abundances on the white dwarf. And they pulsate. So the ones that you can actually see the white dwarf, you can actually look for pulsations. And when there's about 20 of these systems that have pulsating white dwarfs, and you can see that it's very obvious. So this is, 2/10 of basically a few tenths of a magnitude in some cases. So it's easy to pick up. And the period you can see, this is the Fourier transform across many nights. It's not exact. The periods wander a little bit, but this period is very close to 20 minutes. So that's a signature of pulsation. Periods are not exact, but there is a characteristic time scale. But those periods we found can change. So sometimes here at one, I'm seeing all this black bars across the top of my screen. But so you can see that 20-minute period is there, but at other times of the year, it kind of transforms to a longer period that's very close to the superhump period. And this is one of the problems that we do not understand right now, how these pulsations can somehow change into something else. When the system, this is the magnitude at the time, it's a fairly faint system, but the magnitude has not changed tremendously so that the period would change. And we see this also in this 20-minute period in GW Lieb, one of these the high amplitude object that went into an outburst. It had a 20-minute pulse, but sometimes that light curve would change into something close to what would be a superhump variation. And we do not understand this very well. And we actually had K2 observations along with HST. This is a plot here of Boris led this program that many of us were involved in. You can see the 20-minute variation along with a 4-hour variation. This big hump is a 4-hour variation, and the black is the HST data, and HST data showed a very short period. We were following this thing after outburst to follow the pulsations, because when it becomes heated, it moves out of the instability strip, and we were watching it move back in, and it just confounded all theoretical expectations of what pulsation should do after an outburst. And it took a long time. It took basically 16 years to return back to what's normal pulsation mode. So, the white dwarf is very much affected by the outburst. Okay, I'm going to go over very quickly what intermediate polars look like. You can determine the white dwarf spin period and the variability over time. So this is you're seeing the accretion poles of the white dwarf sweep across, and that creates this pulse. The white dwarf is not locked, the spin period is not locked to the orbit like it is in polars, because the magnetic field is weaker than in polars. So the spin period shows up, and the difference in the spin period can be the same time scale as like the pulsations that I just showed you, but the pulsations, remember, were wandering a little bit at different nights, whereas the spin period is stable. So generally the spin period is 1/10 of the orbital period. And you can identify, here are some candidate intermediate polars identified from the shape of the light curves. These is a paper done by Bruce Margon and others from the Palomar Transfer Facility, which a sky survey that took place before the Zwicky one. And they just folded the data, and you can see there's this characteristic hump shape. This is 2 orbits phased, but you can easily get out the period, and this shape is characteristic of IPs. Now, the nice thing that we've been finding recently is that IPs can actually turn off their accretion. And when the accretion turns off, you get a lot more information because that whole stream and disk goes away, and you basically are seeing the underlying stars. So here's Y-wire DO-DROC. For those of you familiar with the system, it has like 2 names. But this is test data. And the test data at the basically this is flux data, not magnitudes. But during the high state, it's kind of, lots of stuff going on, but nothing, nothing really stands out. But when it went into this very low state, decreased by factors of 3 here, this is what the light curve looks like. And you can see during this low that there's a very nice period that shows up. And this is the ellipsoidal variation of the underlying star. So it's information you can get during a low state that is not visible at any other time. And the other thing that's been fairly recent that we've discovered is that the IPs have these very short outbursts. We originally thought maybe they were just some kind of truncated outburst. They last for about 5 hours. And here's 3 of them that was picked up in the test data. The top plot is test data can be taken at different exposure times. So this top plot is data taken at 120 seconds, 2-minute exposures. On the bottom plot is data taken at 20-second of those 3. It happens at the same time. So we can expand. So this is this outburst, and this is this one. And you can see that they last for like 2 or 3/10 of a day, much shorter than a dwarf nova outburst, which typically lasts for several days to several weeks. And so Simone Scaringi has come up with that maybe these are micronova events. And this is, we've been finding these kind of flares, or whatever you want to call them, mini outbursts, micro outbursts, in several of the IPs. We think it's related to the magnetic activity compressing the material so that it can have a thermonuclear flash on the surface of the white dwarf. Now, this is controversial. This is certainly not set in stone yet, and different groups have different ideas as to what is actually causing these flashes, but they are certainly different than a normal dwarf nova outburst. It's another example. Now, it turns out that we also found that what we originally considered just a normal nova-like with a low magnetic field, typical disk, MV Lyra, some of you may have observed MV Lyra in the past. It's fairly bright objects, 12th magnitude when it's in a high state, but then it can shut off. And here's some examples of this is the AVSO light curve in the top here. And the Kepler data was taken in the red here during this very low state that happened at what's now called time 0 here. And this is an expansion, the second plot. So this is 0 to 60. So right when it goes into this low state here. And if you look at day 20, between 20 and 30 here, that's an expansion in this lower plot. And it has these mini things, outburst type things, which Simone has also modeled with what he calls magnetic gating. So whether this is the correct explanation or not, at least it makes sense in terms of this object really does have a magnetic field. We have not been able to measure that magnetic field before in any way, but a magnetic field would allow the material to build up to the magnetic gate and then have an outburst and then recede back from it. And that would be able to cause the behavior that we see. So it's a way of exploring the magnetic field of nova-likes. Now, we can't tell when it's going to enter a low state. That's the problem. But the low states can last for, days to weeks in time. And so if we can get an alert out from AVSO observers, for example, then people can concentrate in looking at the low state. And the low state is when we can actually see the underlying stars as well. So we can get a handle on the temperature of the white dwarf and what the secondary star is. Because usually at the high state at 12th magnitude, it's all just disk that we're seeing. We cannot study the underlying stars at all. Okay, polars and LARPs also have orbital modulations and variability over time. So they also have this big hump structure. They can have eclipses depending on the inclination of the system. This big hump is created by when you're looking at as accretion pole sweeps along your line of sight throughout the orbit. And in this case, in polars, the white dwarf spin is locked to be the same as the orbit. So you just watch the pole sweep by, and that gives you a clue as to what it is. But this modulation in polars, if you follow them for long periods of time, can change. So here's where it's just doing its normal thing. This is hours on the bottom axis, and it shows the normal hump. And then on a different date, it's, that hump has basically disappeared. And we do not understand what's happening here. Either the pole is being obscured by other material, or there could be some pole switching going on. There could be quadrupoles going on. There's a lot of activity in the polars that we don't understand very well. And this is, again, I showed this in the spectral plot, but this is what happens when you have LARPs, low accretion rate polars. The accretion rate is very low. We think it's wind accretion. They show these very broad humps in the spectra. And the spacing of the humps, there's a very simple equation that relates the spacing of the humps to the magnetic field. And so it allows the determination of the magnetic fields. Most of them, the vast majority of the 36 known, are around 60 megagauss. Here's another one. So if the field strength changes, the hump spacing changes, and so the hump can move out of the visible regime into the infrared or into the ultraviolet. So sometimes you don't get this really nice spacing of the humps that you can determine the field that well. And as a function of orbital phase, those humps change. I'm going to leave time here. You can find the 60 megagauss fields basically at different colors. They appear at different places in the color plot. But here are the ones for 60 megagauss. You can see that the colors are very red. G minus R 1.5 and U minus G of 1.5. So those are easy to pick up in sky survey by color. The main reason we want to get orbital periods for the systems is that it helps us to understand the evolution of CVs. We think they come out of the common envelope at long orbital periods and born as CVs. Angular momentum losses move them down an orbital period until they reach some point where the secondary has lost so much material, it's basically a brown dwarf, and it period increases again. The early surveys found the bright ones. So this is mass accretion rate, which is basically brightness, and here's the period in hours. So the early surveys found the bright ones. The later surveys, the most recent ones, are finding the faint ones and helping us understand how many should be in each category. So before the Sloan Digital Sky Survey, the period distribution was large, and we thought, oh, something's wrong, because theory predicted most CVs should be very short periods. But as we went to fainter magnitudes, the period distribution changed, and we're closer to what is expected, but not quite matching what theorists are predicting. The most recent data is coming from Gaia, which is wonderful because it gives us distances, which gives us actual brightness, the luminosity of a source. And one of the graduate students in Berkeley, Ellie Abrahams, recently put out a paper where this is the Gaia, a lot of Gaia data, and this gray plot is the main sequence in colors, Gaia colors, blue minus red, and Gaia G magnitude. And this gray sequence down here are white dwarfs. CVs are basically green. They lie in between the main sequence and the white dwarf because they have a secondary and they have an accretion disk. So they make them brighter than the white dwarfs, but fainter than the main sequence stars. And she's been able to map out lines in here that represent where orbital period should lie for CVs. And so, for example, like this is a line for a period of 3.18. And as you get down closer and closer to the white dwarf sequence, the periods get shorter and shorter. So if you can find your object in the Gaia color plot, you can get an approximate period, and that helps us in our understanding of CV evolution. And so I have to end with what's coming up in the future, 2025 to 2035. There's going to be LSST, which is going to have a wealth of objects. You won't be able to follow, well, none of us will be able to follow the faintest ones that are going to get on to like 27th magnitude, but we will. There will be a significant number of those around 17th, 16th or 17th magnitude. And we will be able to follow them with better time resolution and give alerts for satellite observations and really get a better understanding of CV evolution. So I just want to end with thanks to all of you that have observed CVs, and that database has really helped all of us to understand better what's happening with CVs, and I hope that will continue. Thank you.
Fantastic talk. Thank you so much, Professor Szkody. Excellent. Okay, so we have had quite a few questions come in. We'll go ahead and jump right in with starting with some related to light curves. So we had a question from Hal Heaton who'd like to know if any of the various types of CV waveforms, I'm assuming he's referring to light curves, are correlated with the type of the secondary star in the system. What sort of information can you extract about the secondary?
Well, if the secondary is a low, an earlier main sequence star, then the outbursts tend to be more frequent because the mass transfer rate is higher. So it's very difficult. I mean, you're talking about the shape of the quiescent light curve or the shape of the outburst. I'm not quite sure what the. I mean,
it does not specify in the question, but we can ask Hal to clarify and come back to it if you'd like.
Okay, I mean, you could see, if you see like a ellipsoidal variation in the light curve, you could at quiescence say something about what the mass of the secondary star is, but usually that's all swamped by the light from the accretion disk, so it's very hard to do. In terms of the outburst, the secondary star is an M star, then you're basically into the SU UMA regime, and you basically have super outbursts.
Okay, thank you. So our next question here about light curves comes from Matthias Kolb, who's curious about the small, very, very short-term variations on timescales of minutes seen in cataclysmics like SS Cygni during quiescence. Are those pulsations? What causes those?
No, those aren't periodic. I mean, usually all thing in from disks have some variability that's basically flickering noise. So basically we think it's matter comes across in little spurts. It's not a steady constant stream, and so as each little blob kind of hits, it creates a little burst of light, and so we think that's the source of the flickering, which is not periodic. I mean, if there is a periodic source, it wouldn't be seen in something like SSIG, except maybe near outbursts. There's some QPO things that come in. But if there's a periodic signal at a few seconds, then it would be an IP, because then you're showing basically the spin of the white dwarf.
Mm-hmm.
Okay. But it's usually, I mean, it's really hard to detect if it's not a magnetic system, because the white dwarf is, you can't really pick up the spin.
Okay, thank you. Our next question here, this is an interesting one. Does the accretion of matter from one star to the other affect the orbit of the binary system?
Well, ultimately, the accretion of matter is thought to be one of the possible explanations for the discrepancy in what we think is the angular momentum loss. So as I said, we're getting closer in terms of the periods to what theorists say should be the numbers in each category as systems evolve from long period to short period. But the numbers don't match exactly. And so the discrepancy, there has to be some additional angular momentum losses that are taking place. And every time there's an angular momentum loss over in long-term evolution, it shrinks the orbit. Mm-hmm. And so one of the ways to make this, not happen faster or make it happen faster, it depends on the angular momentum losses that are employed. And one of the suggestions is that the mass transfer is actually causing some of the additional angular momentum loss. So the answer would be yes in the long term, but it would take long periods of time for to notice the effect. And we
Right.
don't know if that's, again, it's a theoretical explanation and there are others. So
Gotcha. Okay. Okay, thank you. So, switching topics a little bit here, we had an interesting question come in from Chris Mahar, referring to the beginning of your talk when you mentioned that, we don't have a actual photograph showing both components of a CV and the mass transfer stream and all that yet. Is there any chance that sub-millimeter telescopes like SMA in Hawaii or Atacama in Chile, could observe some details, angular details within CV systems?
yeah, I did a calculation a couple of years ago, taking the closest system, which I think is like 45 parsecs away, and just looking at the separation of the stars and what it would take. And it was like we were, I think, 2 orders of magnitude off from anything I knew they could do it. So, I don't know what the future will hold, but maybe at some point we will get down to the level that's needed. But they're just very close, and very close systems, and it's just we don't. Well, very close, but they're too far apart that you can't use any of the normal resolution that we can to actually get sizes and actually get pictures of things. So there may be something in the future, and I don't know enough about the submillimeter to say what what will happen. But I've looked at what Lisa would be able to do, and some of the other plans that were made for some of the large space interferometers, and they weren't yet at the point where they could get anything in my lifetime or maybe in the next 100 years. I don't know.
I see. Yeah. Okay, thank you. I
Alma,
do.
I mean, I was hoping Alma or something would be able to actually image like a disc, but it's not in the realm yet.
Right. Yeah. Okay. For the person who asked that question, since you're curious, I will mention that years ago we had a presentation in this webinar series from Dr. Margarita Krofska, who discussed at the end of her presentation a proposal for a telescope. I think it was a constellation of telescopes in space
Yep.
to try and make this kind of observation. It was, as you're saying, nothing right now that can do it, but it was an interesting proposal. So maybe those of you who are interested in it should look up that presentation by Margarita Krofska.
Yeah, I'm hoping it will happen at some point in the future, because it'd be great to get a picture of I mean, all these ideas of what things look like, if that's really true.
Yes, absolutely. That would be so cool. Okay, let's see. Going back to some of the more technical questions. So Enrique Gomez had asked if there could be many IP micronovae events happening all the time, then we're just missing them because we don't have enough monitoring.
Exactly. Yeah. I mean, that's why these space things but they're only pointing at one place in the sky. And so the rest of the year they're elsewhere. And so they're not getting that information. But if they happen, like some of them happen every few days for several hours. So you just need you need an all sky survey that happens frequently enough. I don't know if Gaia would have picked up some of these, because they do, I forget how often, but they don't, I think they only survey, I forget what their time scale for surveying, but yeah, would need a future satellite that does all sky on something like a daily basis, and it would pick up. And it's turning out, I mean, I think there's now, oh gosh, there must be 4 or 5 at least that are now showing these IP flares that we just didn't know about before. So it may be very common, and we just haven't done the monitoring.
Mhm. Great to
And
know.
also, the low states, we're now getting a much better understanding with some of these satellites, how often things are in high states versus low states. Because before it was thought, well, most systems stay in a high state, but that that slide I showed of MV Lyra from the AVSO also shows, there's, they come and go, and we don't know, there just hasn't been enough monitoring of many of these other systems to know, like, what's the normal state. In polars, it was originally thought most polars stayed in low states versus high states. And now I think Paul Mason has done a study of the ones from satellite surveys, and he finds some do more high states than low states. And it's just, we just don't have enough accumulated long-term coverage to really tell what's happening as a general rule.
Okay.
Because we don't understand. I mean, one of the main problems is understanding what is causing the shutoff of accretion. And it's, one idea is that there's these spots that come across the point where the mass transfer happens, and so it stops the mass transfer. But that, I don't think that really fits all the evidence so far. So it's, there's no real explanation. Is it some kind of cyclic activity in the secondary that causes it to withdraw into this Roche lobe to shut off the mass transfer, or what's actually causing that to happen? There's still a lot to be learned there.
Very interesting. Okay. So tangentially related. We had a question that came in here asking, what is the cause of the huge range in magnetic field strengths among populations of white dwarfs?
That is a great question. So, I mean, we were having there was this meeting in the KITP this last year where there's a lot of discussion about magnetic fields. So there's my bird clock going off. And, it's really, we could not come up with what exactly. I mean, the first thing is how is a magnetic field generated? We think it's something that happens in the common envelope stage that creates these high fields. And then there's a difference in, the magnetic fields. They're all high mass objects that have for CVs, the white dwarfs are higher mass. It's all related to what actually happens in the common envelope. Are we just missing some of the other systems that have lower fields, et cetera? And what is actually the magnetic field of most dwarf novae, because we cannot measure them. We think it's probably kilogauss at least. But as apparent in the nova-likes, there must be strong magnetic activity happening. So the answer is we really don't know why some of these systems have high fields and others low fields. It's something to do with their evolution.
Okay,
They
interesting.
all seem to have the same secondaries. There's no real mass difference in the white dwarfs. They're all around 0.8 solar masses. So how do you get this wide range of fields? Well, it's also true for normal white dwarfs. Normal white dwarfs have a large range, and they have very high fields and low fields. It happens in the spin up when the evolution is proceeding, when they're shrinking to become white dwarfs.
Very interesting. Thank you. Okay, so one more technical question here before we switch topics. So Teso Napoleano has asked, what does the slope of the Kurarkin-Parengo relation, I hope I pronounced that right, amplitudes versus recurrence times, what does the slope of that relation tell us?
Well, for the models that have been done, the recurrence time is very much a function of the accretion rate. So if you have a high accretion rate, you've got a short recurrence time versus just takes a long time to build up. And so at the peak of an outburst, the studies have shown that basically when the outburst happens, all the objects reach the same brightness level. So if you start out from a very low mass transfer rate, you're at a very low level. So to reach that peak outburst, the buildup, when it happens, there's going to be a very large amplitude. So it just takes a long time to make the buildup. And then when it does build up, the jump to the high outburst state is very large. So I mean, that's just telling us. So the relation is telling us just, what's the state of the quiescent disk in these systems, and whether and that's related to the mass transfer rate. And some of the models, John Canizzo was trying to model the recurrence time versus amplitude, and he had to have, it's all dependent on, the outbursts are very much dependent on a parameter called viscosity. And that changes from the quiescent level to the outburst level. And for the systems with the longest recurrence times, he had to have a very low viscosity level for the system, which is just related to whatever is causing the viscosity. And there's various models for that, but it's very low in the long recurrence times objects, which just translates to very low mass transfer rates. I don't know if that answers what they were asking.
I think well, it answered the question for me. Hopefully it did for Teso too, but it was a good answer. So thank you. Okay, so now we have kind of a more general question here from Michael Meadows. Michael would like to know if you can point him towards any current written review that covers the vast taxonomic zoo, which you've just discussed in your presentation, and some of these ideas that you offered as explanation. Is there a review for further reading?
Let's see, a review of all CVs. Oh gosh, the thing I use, my textbook is Warner's book on cataclysmic variables, which dates back to, I think, 1985.
Okay.
But it basically has gone over the basic categories and the objects that were known at that time. There's also, these books are maybe in some of the libraries. I don't think it's an online version, so I'm trying to think of a review that would be in like one of the online. I mean, there's been reviews of like IPs. Koji Mukai has written reviews of IPs. There's been reviews of pulsating white dwarfs. Most people now are doing reviews of individual groups of objects rather than the whole field of cataclysmic variables, because it takes like a book to go through.
Right.
I mean, I went over time in mine just trying to talk about objects here, but to go through the whole classification and everything. But I mean, the AVSO has basically a pretty good summary of different kinds of variables, right? I mean, the categories. There used to be a cataclysmic variable page that talks about the various kinds, right?
Yes, so we have a cataclysmic variables observing section that has some educational material on their webpage. And we also have the VSX database has a help page that defines all of the various subclasses, at least the ones that are entered in VSX. So those are both resources that give an overview.
Right. I mean, the thing is, the AVSO is such a great database because you can put in, if you know, like a type of object or the one that represents that type, you can just get its light curve and look at it and just see
Yeah.
what the shape, what it's telling you. Although the orbital stuff is harder. So I mean, the advantage of the vast database is that you can actually search it. Well, if you have enough points in the database, then you can pick out the hour kind of variability that's taking place. And that's what we found from the sky surveys, that it doesn't matter that you have cadence for a couple hour period. It doesn't matter that you have the cadence of a couple hours. You can, if you have a long enough database, you can fold it back and it will pick up the period.
Mhm. Yeah, it is a marvelous resource. Thanks for saying that. Okay, so speaking of observations, we had several different questions come in on the topic of what AVSO members can be doing to contribute to the study of CVs by making observations. So first, just a question from Walt Cooney, who's actually currently the leader of that cataclysmic variables section, which I mentioned. Walt would like to know which types of CVs you would prefer for AVSO members to be monitoring most frequently.
Well, I would say right now the IPs would be good to
Okay.
find more. How many of them do they all show this kind of behavior? Or is it dependent on some characteristic like I mean, most of the IPs have longer orbital periods. Is that the characteristic that makes the mass transfer strong enough to push these magnetic flashes, if that's what it is, to happen. And is it something that's apparent in all of them, or just, you know, some subset that would give us a clue as to what causes those flashes?
Mhm.
I mean, the other thing is just, you know, that the activity level that I showed for the MLS source, the Sloan source that had the super outburst and activity level change before the outburst versus after. I mean, just that's something that monitoring on a day-by-day basis could over a long period, over months, could reveal more. I mean, we just don't have a good database of that activity that's kind of outside a normal outburst. Those were less than a magnitude changes, so they weren't a real outburst. So there's something else happening in the disk, and we just don't have a good handle on you know, that kind of activity level. So it would be monitoring short orbital period systems that have super outbursts and monitoring the activity level. I mean, these could be bright ones. I mean, I'm sure there's some that are around 17th magnitude that could be monitored on a daily basis to look at, you know, how common is this kind of activity level, these like mini flares, and they're not disk outbursts, but there's something going on, not periodic as far as I can tell, to see if that's a common phenomena or not.
Mhm. Okay, that's great to know. Thank you. And here's a question from David or Dens. This is a more general context. So once projects like LSST become active and we have this avalanche of data coming from the survey, what kind of amateur observations do you think will be the most useful to complement LSST and to continue your type of studies?
Well, there's, you know, because there's going to be systems that, so the current surveys have picked up most of the short outbursting systems. So what we're now going to pick up a lot of are the ones that have outbursts that were not known before, the long recurrence times, the ones that are 20 or 30 years. So it's going to be, once those, you know, once those are picked up, you know, what are the characteristics of those systems that you can monitor while they're still bright? Because we're not going to be able to get much information on most of the LST sources when they're faint, because they're just beyond the limit. But I think also the blue filters are going to be very important for ground-based studies. LSST is really downplaying the blue filters because of the lack of sensitivity, especially a U. If anybody can get a U filter, that's, you know, for hot white dwarfs, for most CVs which are hot, there's very little information now coming up because most observations are done with red CCDs or unfiltered CCDs. So for those that can actually get some information in the blue, because the hotspot shows up better in the blue, the white dwarf shows up better in the blue, you know, even just the variability over an orbit over a short period of time in the blue would be useful. There are there's a couple of foreign, so LSST is going to have a lot of partners contributing because the US would not allow cash contributions. So the partners, some of the partners are going to be using like 1 meter telescopes. And that's one of the things too that they're going to be trying to do is do some short time scale variability, because the LSST cadence is going to be once every 3 days. So for the ones that do outbursts, just following them on a daily basis is going to be a contribution, because that's not going to be there in the LSST data.
Mhm. Okay, thank you. So we only have a couple minutes left in the Q&A. I think we'll go ahead and we have a couple questions here about spectroscopy and one about dwarf novae light curves. So starting with the spectroscopy, Lawrence Seven was asking about if there are any spectroscopic lines other than the helium-2 line, which are a dead giveaway of a cataclysmic variable, you know, something that wouldn't be found in a planetary nebula or a symbiotic or something else masquerading as a cataclysmic.
Okay, well, the Balmer lines are a good indication. I mean, in a planetary nebula, the lines are much thinner in width, and the ratio between H alpha and H beta is very large. In a cataclysmic variable, there's what we call a flat Balmer decrement. So the flux of H alpha and H beta is pretty much the same. That's because the conditions in the disk are very much denser than the conditions in a planetary nebula. So if you can get H alpha and H beta, because they're emission lines, so that's good, because emission lines you can actually go fainter because you're not getting worried so much about the continuum. If you can get the ratio of H alpha to H beta, that would be useful. I mean, planetaries have different, I mean, they have forbidden lines, et cetera, that are not apparent, that are not present in CVs at all. So basically CVs are Balmer emission plus helium-1 emission. And then the clincher is the helium. For magnetic, for separation of magnetic versus non-magnetic, it's the helium-2.
That's really great to know. Okay. And relatedly, there was a question from Gisu Happy who asked, how can we be sure that the helium to 4686 line is caused by a shock? You know, why is that? Why is it that when you see that, you know for a fact that there's a shock in the system?
Well, it just, helium-2 takes a very high amount of energy to produce it, much more than the Balmer emission lines.
I
And
see.
so that means the conditions where that happens is different. Now, it doesn't have, I mean, it can be like from a boundary layer, because helium-2 is also present in what I didn't cover this aspect, but there's SW6 stars, which are between 3 and 4 hours orbital periods, and they have they're disk systems, they're nova-likes. We don't know if they're magnetic or not. They don't show any indication. They're not IPs. But they also have the helium-2 line. So it's possible to have a helium-2 line present in these systems. So if the orbital period is 3 to 4 hours, you have helium-2, and it doesn't have a spin period. I mean, a spin period evident that would be evident in an IP, then it's probably an SW6 star. But it's probably coming from the boundary layer, because the accretion rate is so high that creates basically a shock at the boundary layer all around the whole ring, like of the white dwarf, rather than in one small area of an accretion pole. But you just have to have those high excitation conditions, high energy conditions for that helium-2 line to appear. Because it's present in like X-ray binaries, and in all high excitation sources have it.
Okay, thank you. So our last couple of questions here are about dwarf novae. First, regarding dwarf novae like SS Cygni, why is it that they are bimodal? You have super outbursts, you have regular outbursts, not really in between, it seems like. What causes that bimodality?
Oh, that's because of the tidal effects. So you're going to have super outbursts when you're in the short period regime and have the tidal effects coming into play. Whereas the longer period ones, they're separated enough that the tidal effects are much less. So they don't have the super outbursts, which is what it takes to reach the regime of the disk being at the, it's a resonance of the periods in the disk with the secondary that causes that. Once it reaches that point, the disk becomes elliptical. Whereas in a SS Cygni disk, it's, that's not taking place because the accretion rate's too large and the separations are larger.
Okay, thank you. And then our last question here about dwarf novae comes from Sam Lee, who asks, for some dwarf novae, the orbital period can be observed as a periodic oscillation during the super outbursts. What is the mechanism behind that?
Sorry, say that again. This is the super hump period? Is that what they're
So
asking about?
the question says that in some dwarf novae, the orbital period can be observed as a periodic oscillation during the super outbursts. And
Oh, okay.
what is the mechanism that causes it to appear in the light curve in the first place?
Okay, so right in the beginning of a super outburst, you get this double hump variation, which is at the orbital period, and then the super humps start, which is the longer period because the disk has become elliptical in shape. So in the beginning, in beginning stages when it shows up, I believe it's because the matter is coming in so fast, it's like overflowing the disk and creating like two spots. And so that creates a double hump structure in the light curve. And if you do like Doppler tomography of disks, they have this like spiral structure that develops in the disk as the super outburst or the outburst happens. And so that structure, which is, you know, basically caused by the accretion rate overflow being so large, I think it basically causes this like almost like a, you know, a ring structure inside the disk, and that can cause these humps to appear. And then once the disk becomes kind of homogenized and elliptical, then the super humps, it reaches that resonance point, then the super humps take over versus the orbital. And I forget, I think it's like 1 or 2 days, maybe, or maybe less than that, that you see the original orbital period. So you have to catch it right at the right time to see that before
Okay.
the super humps develop. I think that's what you're referring to.
Okay, thank you. That's fascinating. So we are at this point out of time for questions. We do have, I noticed, a number still pending that are excellent questions and I think would be very well suited to the cataclysmic variables section of the AAVSO. So to everyone who still has an unanswered question, I highly encourage you, go to our website, visit the forums where there's a cataclysmic variables section, and there's information there on the group itself and the meetings that they have regularly. You can either post in the forums or you can attend one of the meetings and ask there. But that's a really great group where I think I'm scanning through the question list right now. I know people in that group who would be able to help you with these particular questions that are left
Well,
over, and it's a great place to get started. So,
Lauren, do you save the questions? Can you save the
yes, we do have a log of the questions, I believe, in Zoom.
if you want, you can send those to me and I can answer them. But I guess there's no email attached, so I can't
There
answer them
is,
usually.
yeah, unfortunately, there's not an email attached. Some of these questions have names attached, some do not. So, I think that probably the best option is to either, like I was saying, go to the Cataclysmic Variables forum and ask there, or Professor Szkody, if you would like to answer some further questions, then perhaps people could reach out to you at your institutional email and email you a
Sure.
couple of questions.
Yeah, it's just Szkody@uw.edu.
Excellent. Thank you so much for that offer. That's great. Okay. So with that, I'm going to go ahead and put up our closing slide here. Okay. Professor Szkody, thank you so much for sharing your time and your knowledge with us today. That was an excellent presentation and a really informative Q&A. I know that I personally am going to be going back and rewatching the recording at least once to get as much as I can out of it, because that was really fantastically done. Thank you.
It's great to see so many people interested in CVs.
Yes,
It's a
isn't it?
wonderful field to work in. Thank you.
Thanks. Okay, before we close, I would like to express our sincere gratitude to our 2024 series sponsor, Voice Astro. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. All right, as a reminder, registration is now open for next month's free webinar scheduled for May 11th. This one will be an interactive session where you can join the Executive Director of the AAVSO, Dr. Brian Kloppenborg, as he explores the intricacies of photometric filters, photometric transformations, and how you can use those to maximize your photometric accuracy. To learn more and sign up for the webinar and save your spot early, you can visit our website at aavso.org/webinars. I hope to see you there. To those of you who are out there in the audience right now, wherever you are in the world, I would just like to say thank you. Your participation in our webinar series, and really all of our programs, is what allows us to keep growing, keep educating, and keep making an impact on variable star science. So, thank you. We really couldn't do it without you. Now, fortunately for people like myself who would like to have a review, today's broadcast has been recorded. And if you'd like to go back and reference it, you can find it on our Facebook page, where it will be automatically uploaded in a matter of minutes. Pretty soon, we'll also upload it to our YouTube channel, where it will join an enormous library of educational videos. We've been running these webinars since 2020, and cataclysmic variables have been mentioned a couple of different times, both research and observing them. You can find those videos in our library on YouTube by searching for the username AAVSOHQ. When you leave today's webinar, you should be automatically redirected to a survey displayed in your browser. I would really appreciate it if you could please fill out the survey, let us know what you thought about today's presentation, and let us know what we can do better next time. All right, to close, I would like to express a final sincere thank you to Professor Paula Szkody from all of us here at the AAVSO. We appreciate you. Right. With that, thanks everyone for tuning in, and see you all next time.